Welcome back to this video series on electronic circuits, and in this video we're going to talk about electron flow versus conventional flow, and then we'll talk about voltage, power, and energy. So what is electron flow? Electron current flow is the flow of negatively charged particles through a conductor, and in reality this is exactly what is happening in the electronic circuits. You have negatively charged particles, or electrons, which flow from the negative terminal of the battery to the positive terminal of the battery. So why does this happen? We know that like charges repel and opposite charges attract. So if you have two particles and they are the same charge, they're both negatively charged, let's say, they will repel each other. If you have two particles and they are opposite of each other, they will attract each other. So when we look at this circuit down here below, the reason why electrons flow from the negative terminal of the battery to the positive terminal is because this negatively charged terminal will repel these electrons. So the electrons will begin to flow around the circuit like this. While at the same time, this positively charged terminal will attract the electrons. So you get electrons flowing from negative to positive in a circuit. So what is conventional current? Conventional current is the flow of positively charged particles, or protons, through a conductor. Positive charges flow from the positive terminal of the battery to the negative terminal of the battery. Why does this happen? Again, we know that like charges repel each other and opposite charges attract. So for instance, if this is the positive terminal of the battery and this is the negative terminal, and you have positively charged protons that are flowing through the circuit, we know that this positively charged terminal will repel around in this direction, while at the same time this negatively charged terminal of the battery will attract these protons, or positively charged particles. So you get positive charges flowing from positive terminal of the battery to the negative terminal of the battery. Does this happen in real life? Is this actually what is happening in electric circuits? No, because in reality it is the flow of electrons instead of the flow of protons or positively charged particles. Mathematically, the flow of electrons from the negative terminal of the battery to the positive terminal is the same as the flow of positive charge from the positive terminal of the battery to the negative terminal of the battery. And so conventional current will be used throughout the rest of this video series. It will also probably be used throughout your career as an engineer. So now let's talk about voltage, or potential difference. The definition of voltage is the amount of energy required to move a unit charge, or to move 1 coulomb of charge. And this is measured in volts. So when we think about 1 volt is equal to 1 joule of energy for every coulomb of charge. So again, the higher the voltage, the more energy you have per coulomb of charge. So if we have 12 volts, that would be equal to 12 joules of energy per 1 coulomb of charge flowing through the circuit. And when we measure voltage, we always measure it across a circuit element. So for example, here at the bottom we have a circuit element. It has two terminals. It has a positive terminal and a negative terminal. And it's also labeled that there is a 9-volt potential difference between those 2 points, or between those 2 terminals. So what exactly does this mean? It means that point A, since it is the positive terminal, has 9 volts higher in potential energy than point B, or terminal B, which is the negative terminal of this circuit element. So again, when you measure voltage, always measure across the element. Since we've talked about current in the previous video, and we've talked about voltage, now let's consider the water pipe analogy. In this analogy, I'm going to refer to this circuit as the water circuit. I'm going to refer to this circuit as the electric circuit. In the water circuit, we have a pressure pump, which is responsible for pushing the individual water molecules. And in the electric circuit, we have a battery or some voltage source, which is responsible for pushing the individual electrons. And in this water circuit, we have pipes, which directs the flow. And in the electric circuit, we have a wire, which directs the flow of the electrons. Now again, in the water circuit, Each individual water molecule is moving through the pipes, and the combination of all of these moving through the pipes gives us a current or a flow of water. And in the electric circuit, we have, again, the electrons that are moving, and the combination of all of these electrons moving through the conducting wire gives us an electric current. So now let's talk about power, or electric power. What is power? It is the time rate of expending or absorbing energy, and it is always measured in watts. So we have 1 watt of power is equal to 1 joule of energy per second. So what does this mean? If you have a circuit element, let's say it consumes 12 watts of power. This means that that particular circuit element will consume 12 joules of energy per second. And the way to mathematically describe this relationship is that power is equal to the time derivative of energy, which again states that the power is equal to the time rate of expending or absorbing energy. But oftentimes in electrical engineering, we have power is equal to voltage times the current. So where does this equation come from? Well, we know that a voltage is equal to dW dQ, and we know that the current I is equal to dQ dt. And we know if power equals dW dt, and we say is equal to voltage, which is dW dQ, multiplied by the current, which is dQ dt. The dq's cancel out, and again we have dW dt is equal to dW dt. So that's where the equation power is equal to voltage times current comes from. With respect to electric circuits, this equation tells us that if we know the voltage across a circuit element and the current through that circuit element, then we can calculate how much power that element will either supply or absorb in the circuit. And when we talk about power being absorbed or supplied by the different circuit elements in a circuit, it's always important to understand the law of conservation of energy. And what this says is that the sum of power in a circuit must be equal to 0. So if we look at this circuit in the top right, we have 5 circuit elements. We know that the total power in this circuit must equal 0. So when we write an equation for that, we know that the power of circuit element 1 plus the power of circuit element 2 plus the power of circuit element 3 and so on must equal 0. This would obey the law of conservation of energy. So how do we know which elements are supplying power or which elements are absorbing power? So to do this, we use the passive sign convention, which says if current enters the positive terminal of an element, the power is P equal to positive voltage times current. And it says if the current enters the negative terminal of an element, the power is P equals negative voltage times current. So when calculating this, I suggest to pick which one of those and stick with it. What I like to do is I always write the current entering the positive terminal. And if the current enters the positive terminal, I always use positive voltage times current. Now, before we do a couple example problems, if we have current flowing this direction, and it is, let's say, 3 amps, it is the same as, say, a negative 3 amps flowing in the opposite direction. These two are equal. 3 amps in one direction is equivalent to negative 3 amps in the opposite direction. So you can always write the current entering the positive terminal. So for our first example, we have a positive terminal and a negative terminal. We know the voltage and the current of this element. We want to know the power this element is either supplying or absorbing. So to do that, again, I always write the current entering the positive terminal. So in this case, it is entering the positive terminal. So the power would simply be P is equal to V, which is 4 volts, times I, which is 3 amps. So we know the power would be 12 watts. And if the power is positive, that means it is absorbing or consuming power. So example number 2. Again, we want to know the power that this element is either supplying or absorbing. So again, I always use P is equal to positive VI, and I always write the current entering the positive terminal. So we know the power is equal to positive the voltage, which is 4 volts, times the current entering the positive terminal. So we see that the 3 amps, the current is actually leaving the positive terminal. So as I mentioned before, we can rewrite that current as negative 3 amps, but flowing in the opposite direction. So I can write negative 3 amps, which is flowing into the positive terminal. So P is equal to positive 4 volts times the current entering the positive terminal. And again, the current would be negative 3 amps since it's in the opposite direction. So the power would be negative 12 watts. And because the power is negative, we know that it is supplying power. So for example number 3, again, power is equal to positive voltage, which is 4 volts, times the current entering the positive terminal. So if we see the direction of current, it is in fact entering the positive terminal, so we would just write 3. And that would give us a positive 12 watts. And because it's positive, we know it is absorbing that power. And for our last example, again, we want to know the power. So power is equal to positive voltage, which is 4 volts, times the current entering the positive terminal. We have 3 amps leaving the positive terminal. Therefore, we can rewrite that as the negative 3 amps entering the positive terminal. So we multiply that by negative 3. And we get power is equal to negative 12 watts, which again shows that it is supplying power. Let's talk about energy. What is energy? Energy is the capacity to do work measured in joules. So what does this mean with reference to electrical energy? So when we talk about electrical energy, it has 2 types. One is kinetic energy, which is electric kinetic energy. And the second one is electric potential energy. So what's the difference in these two? Again, as from a previous video, we know that current is the flow of electrons through a conducting wire. So these electrons are being pushed, they are being moved. And we know that when electrons, these molecules or objects are being moved, there is kinetic energy behind them. So kinetic energy in an electric circuit is caused by the movement of electric charges. So what is electric potential energy? It is defined as the total potential energy 1 coulomb of charge will have. So for example, if we have a battery and we have a positive terminal and a negative terminal, and we know that the voltage across this battery is, let's say, 9 volts. What does this mean? 9 volts is equivalent to 9 joules of energy per coulomb of charge. So when we think about a battery and it's by itself, it's not connected in a circuit, it is said to have potential energy. So it has 9 volts of potential energy because there's no work being done yet while the battery is by itself. But it has the potential to do work, or it has the potential to move those electrons if connected in a circuit. That's why a battery is said to have a potential difference, or it is electric potential energy. So from the previous slide, we know that power is equal to the time derivative of energy. Therefore, we can integrate both sides to come up with an equation for energy with respect to power. So if we know power, then we can integrate it from a certain time interval to come up with how much energy was consumed during that time. So for example, Let's say we have a circuit element and we know that it consumes 12 watts of power. That means it is consuming 12 joules of energy every second. And we want to know how much total energy this circuit element consumed in 10 seconds. So how would we find the total energy consumed in 10 seconds? Well, we know the total energy is equal to the integral from 0 to 10 seconds of the power. So the power for this particular case is 12 watts dt. So if we integrated that, we would end up with 12t evaluated from 0 to 10. And then we would have 12 times 10 minus 12 times 0. So we would have 120 joules of energy was consumed in 10 seconds. Oftentimes, your electric companies measure energy in watt hours, where 1 watt hour is equal to 3,600 joules of energy. So where do they get this number from? We know that 1 watt of power is equal to 1 joule per second. If we multiply the second to the other side, we have 1 watt second is equal to 1 joule. Therefore, 1 watt hour is equal to 1 watt times 3,600 seconds. 3,600 seconds in 1 hour. If we substitute 1 joule per second into this 1 watt, we have 1 watt hour is equal to 1 joule per second multiplied by 3,600 seconds. And we know the seconds will cancel out, and therefore 1 watt hour is equal to 3,600 joules of energy. This was the basics with respect to electron flow versus conventional flow, voltage, power, and energy. So in the next video, we will do example problems related to voltage, power, and energy. Thanks for watching.